So hello everyone, thanks for joining us today. For today's sums talk, we have Dr. Retha Heymann, and she'll be telling us about the Perron Frobenius Theorem and the PageRank algorithm. Just a little bit of background on her. She did her master's at Stellenbosch and then did her PhD in Germany. And now she's researching functional analysis with projects related to spectral theory, operator semigroups, operator theoretic aspects of ergodic theory, and a special interest in multiplication operators. So welcome, Doctor.
All right, thank you. Okay, so I would like to talk about the PageRank algorithm and the Perron Frobenius theorem. So I am not an expert on this, but I do think it's very interesting. And the Perron Frobenius theorem is related to the spectral theory, which I normally do on infinite dimensional spaces, but now this is for finite dimensional spaces, and then it's more understandable and also has a very nice application to the PageRank algorithm. So it's possible that some of you know more than I do about some aspects of the PageRank algorithm, but I'm going to try to explain to you, at least hopefully, how eigenvalues are related to the fact that we know that the PageRank algorithm will always work. And so I hope that there's something new for everyone. So the PageRank algorithm was developed by Larry Page and Sergey Brin at Stanford University in 1996. And the name PageRank is supposed to be a play on both the surname of Larry Page and the fact that it's related to web pages. And the PageRank algorithm, I think it's widely accepted that it contributed hugely to the success of Google. So Google used it early on, and it's still using some version of it, but today I believe no one knows exactly how Google determines the ranks of the search results, but the PageRank and the idea behind it still plays a role. And so I'm going to try and explain maybe a very old and simplified version of the PageRank algorithm. And then we will also need to know what an eigenvalue is in this talk. So I know that this talk is supposed to be understandable by undergrad students. Now, if you are a first-year student, you will not know what an eigenvalue is. If you're a second-year student, I don't think I'm not sure if you've already covered eigenvalues, but I will quickly define what an eigenvalue is. So if we have a matrix, first of all, I want to talk about eigenvalues now. So if A is a square matrix and lambda is a complex number, so then we call lambda an eigenvalue of A if there exists a non-zero vector x such that Ax is equal to lambda x. And then we call, so if this is true, we call lambda an eigenvalue of A, and x is called an eigenvector corresponding to lambda. All right. So this means A is a matrix, X is a vector. It must have the correct size that we can multiply A with X, and then the vector we obtain must be a scalar multiple of X. And the set of eigenvalues of a matrix A we will denote by sigma of A. So this is notation, and this we call all the set of all complex numbers such that lambda is an eigenvalue. And it's also very important here to denote the so-called spectral radius of A, and that is just the maximum of the set of moduli. We take the modulus of lambda, the eigenvalues, and then we take the maximum of all of these non-negative real numbers, and that's the spectral radius. So the maximum, the absolute value of lambda, such that lambda is an eigenvalue of A. So every matrix A has eigenvalues, at least one eigenvalue, and if this is the complex plane, then this is the spectral radius. That means that all eigenvalues lie inside this circle with radius, the spectral radius. Can also be on the boundary, on the circle itself. Okay. Small example, let's quickly do the matrix 2, 1, 3. If we multiply this matrix with the vector 1, 0, we obtain 2, 0, and this is equal to 2 times the vector 1, 0. So 2 is an eigenvalue of this matrix, and the vector 1, 0 is an eigenvector corresponding to 2. All right, now enough about eigenvalues. We'll get back to them in a minute. We now want to quickly talk about the idea of the PageRank algorithm. So, if we have websites, different websites, they link to one another. And the idea of the PageRank algorithm is that a website will be visited more often if there are more pages linking to that website. And also, if the pages linking to that website are visited more often, then that will also increase the popularity of that website or the importance. And the PageRank algorithm wants to assign some positive real number to each website, and then they can use this number to obtain a ranking so that they know which pages should appear first in their search results. Right, so basically, let's try to look at a small example of what this could look like and what this could imply. If we have 4 websites or web pages, let's call them W1, W2, W3, W4. And they link to one another. So let's say website 1 links to websites 2 and 3. Website 2 links to website 3 only. And 3 links to website 1, 4, and 2. And website 4, links only to website 2. So what we see here, so I mean outgoing links, obviously, when I say links to now. So this, what we see here, is something which we can see as a graph in mathematics, a directed graph, which it has 4 vertices, as we say, and arrows between. So some of these are connected, and there's a direction of the connection. So it events from the one to the other one. It's a directed graph. And this particular directed graph is what we call strongly connected. I'm just mentioning it now so that we can remember it later. And that means basically that if we start at any 2 websites here, or vertices, are linked by following the arrows. So we can get from website 1 to website 4, 2 or 3 just by following links to other pages, and there will be a chain from one page to any other page. We call this strongly connected. And now we are basically going to assume that if someone is surfing the web, then they will follow links from page to page, and they will do so quite randomly. So if there are 2 links going from 2 outgoing links from one page to other pages, then the probability of following any one of those links will be a half. So in this case, this one example, the probability of moving from website 1 to 2 will be a half. Well, if we are at website 1, and also moving to website 3 will be a half as well. And so now we can assign the probabilities obviously to all of these, all of the pages which have outgoing links, and that is the case in this example. And now we somehow want to assign an importance somehow to each website, and it should be related to the number of links pointing to that page, and also how important the pages are, where the links come from. And we will write down, we want the number, the PageRank number really, for each page to satisfy the following. We want x1, that should be the rank number of one, that will just be some real number. And in the end, we want to compare all real numbers, and the largest one will be the page which is the most important. Then, so x1 should be equal to, okay, we're going to assign a number x1, x2, x3, and x4 somehow to each of these pages. And x1 should be equal to the sum of this importance number of the pages pointing to x1, and in this case that is just page 3, so I don't even need to write a sum. Page x1 will be equal to x3, and we should multiply this by the probability of moving from page 3 to page 1. So this must be 1 over the number of outgoing links from website 3. And I'm going to use this notation for this. O3 means the number of outgoing links from page 3, and absolute value means, sorry, the O3 is the set, and the absolute value means the number of elements in the set. So I'm going to call OJ is the set of outgoing links from page J, and absolute value means the number elements containing the set. Okay. So basically, page 1 should derive its importance kind of from page 3, because that's the only page pointing to page 1, linking to page 1. And then we want x2 to be equal to, now x2 has 3 pages linking to it, so it will obtain some importance from each of those pages. It will have some from page 1, and we multiply by 1 over the number of outgoing links from page 1 plus x3. Again, we need to multiply by this 1 over the number of outgoing links from this page, and so on. x4 and x3 is that has 2 pages linking to it. x1 and x2 are the numbers which will contribute, and we need to scale them appropriately. Oh, sorry. Like this. Okay, now this we can write in matrix form. This set of equations, we can write this as the vector x, which has components x1, x2, x3, x4, is equal to matrix A times the same vector x. This is what we want, and the matrix A is the link matrix, or the transition matrix, if you think of this as a stochastic process, really. And in this case, okay, A will be the matrix 0, 0, okay, 1 over 3, 0. So I suppose, I don't know if it would have been more clear if I just wrote the numbers directly, but 03 is 3, so this would be 1 over 3. Is this right? Yeah. And then similarly, we can do all of the others. Then we will have a half, 0, a third, 1, a half, 1, 0, 0, and 0, 0, a third, 0. Okay, 1 over 3. So basically, these numbers, x1, x2, x3, and x4, which we are looking for, and which the idea of this algorithm relies on, is this vector. This is given by an eigenvector corresponding to the eigenvalue 1 of the matrix A, because we want to find these numbers x1, x2, x3, x4. We really want to solve this equation. We want to find an x, and that means we want A to have an eigenvalue 1, and then we want to find a corresponding eigenvector, which should hopefully contain real numbers as entries, so that there's a clear way of ordering them, right? Now, fortunately, in this case, that will happen. This matrix does have 1 as an eigenvalue. If you would calculate the eigenvalues of this matrix, you would obtain 1, 0, minus a half, minus I over 2, and minus a half plus I over 2. So 1 is an eigenvalue, fortunately, and we obtain an eigenvector corresponding to 1 here, which will be equal to 1, 5/2, 3, 1. And this is not a normalized eigenvector. We would normally like to normalize it so that the entries sum up to 1. And we can do that by saying we multiply by the scalar of 2/15. Then the entries sum up to 1. But this shows us that these numbers for this example will be equal to x1 is 2/15, x2 is 5/15, x3 is 6/15, and x4 is 2/15. So the most important page in this sense is web page 3, and then web page 2 and page 1 and 4 are equally unimportant in this using this kind of argument. Right, so yeah, we can solve this. We can also obtain a ranking. But the question is really, is there always a solution? And the answer is yes, but not. We need a few more assumptions really, and we need to also change the algorithm a little bit. So the algorithm, I'm saying, I haven't spoken about the algorithm yet, but Google's algorithm, the PageRank algorithm, sorry, uses the idea that if you start with some vector, so you assign some number to each page, and you might start by assigning a quarter to each page. Here you have 4 pages, and then you start doing iterations from page to page, and you see what happens, how often each page is visited. If you randomly move through from page to page in this way, and then you hope to obtain convergence to some kind of vector. And yeah, so as you move from page to page, you carry some of the number with you to the next page. That is how the PageRank algorithm is explained. So if you would move from page 1 to 2 or to 3 here, if page 1 is x1, then you would carry half of x1 to page 2 and half of x1 to page 3. And in the algorithm, that literally happens, and that changes the numbers. And as you go through iterations, you want to obtain some kind of fixed vector in the end, where as you keep moving from page to page, and you just stay in the same, with the same ranking, basically. And that is related to fixed states of Markov processes. And this matrix A, which we see here, is also something which we call a column stochastic matrix, because every column sums up to 1 here. And because this is a column stochastic matrix, we also know, one can deduce from that, that 1 will be an eigenvalue. But the problem is, we don't know if there might not be other eigenvalues with modulus 1 as well. If it is a column stochastic matrix, we also know that the spectral radius will be 1. All of the eigenvalues will have modulus less than or equal to 1. But there might be other eigenvalues on the unit circle then, and because of that, you don't necessarily, that will imply that you don't necessarily know that you will have convergence to a fixed state if you start with some random vector. So you will have convergence to a fixed state. Basically, it comes down to taking exponents to powers of the matrix. So if you take the matrix A to the n and you apply this to some vector, you want this to converge to some vector. Let's call this x0, that's like the initial state, and then you want it to converge to some vector x. And that vector x should also be an eigenvector corresponding to the eigenvalue 1. And you will have this convergence if you know that 1 is a so-called dominant eigenvalue. And that means that 1 must be an eigenvalue and all other eigenvalues must have modulus strictly smaller than 1. And the eigenvalues have a real influence on what happens when we take powers of matrices and what happens to the convergence. And if we have 1 as a dominant eigenvalue, then the convergence will be guaranteed. And this is, if you think of diagonal matrices, then that is clear. Well, it will be so for that case, because if you have, diagonal matrices, then you only have entries on the diagonals. So say we have like lambda 1 and lambda 2 and just a 2 by 2 matrix, and now you take power of this matrix, then this will just be equal to lambda 1 to the n and lambda 2 to the n, 0, 0. And now if the modulus of lambda 1 or lambda 2 is smaller than 1, then you will have convergence to 0. So if both of them are smaller than 1, then this whole thing will just converge to 0. But say now the modulus of lambda 1 is equal to 1, then this might not converge. It might, you might obtain, if the modulus is equal to 1, but it's a complex number, then you will see you might have some periodicity, but you will not have convergence to a fixed number. But if lambda 1 is also equal to 1, then this will just converge to 1. Okay, and if the modulus of one of these eigenvalues are greater than 1, then you will also not have convergence, because then you will have the modulus of lambda 1 to the n getting greater and greater. So then there will be no convergence. And this is for diagonal matrices, but we can use this kind of argument also for more general matrices with eigenvalues, because every matrix is similar to what we call a Jordan normal form, which is a diagonal matrix plus a nilpotent matrix. And if we are going to take exponents of such matrices, then it's really going to be a diagonal matrix, which determines whether or not we have convergence if we take a power and let the power go to infinity. So I'm just mentioning it, I'm not giving details here, I'm just trying to say that the eigenvalues really influence whether or not we have convergence, and we need one to be a dominant eigenvalue to ensure convergence. Okay, so we want 1 to be a dominant eigenvalue of A. Now there is a scenario where we know we will have a guarantee that 1 will be a dominant eigenvalue of A, and that is if we know that A is a strictly positive matrix. And Perron Frobenius tells us that. So for Perron Frobenius theorem, it does have a version for non-negative matrices, but the version for strictly positive matrices is that if A is a strictly positive matrix, I'm going to just write greater than 0, and that means each entry is a real number greater than 0. Okay. Then also, if we, because of the situation where A will be columns stochastic, let's also include this in our assumption. So, and A is column stochastic, which means that the spectral radius will be smaller than or equal to 1, or actually equal to 1, then 1 is a dominant eigenvalue. Of A, and also it has a strictly positive eigenvector. And that is also good news in terms of the page ranking algorithm, because you would like, it is useful if we could obtain numbers which are all strictly greater than 1, real numbers, greater than 0, sorry, and real numbers. And also this this strictly positive eigenvector will belong to an eigenspace which is one-dimensional. So it's one-dimensional eigenspace. And that's also a good thing, because that means that the eigenvector will be unique if we normalize it. So if we take this eigenvector and we want one which has which the entries sum up to 1. It has strictly positive entries and the entries sum up to 1, then that will be unique. And that means we will, if this can be applicable to the page ranking algorithm, the link matrix really, then we will definitely obtain a solution. We will obtain some ranking vector and it will be unique. Okay, and I would like to do quickly show why we know that in such a case, if A is strictly positive, we know that 1 is a dominant eigenvalue. Well, it's an eigenvalue. Why do we know that it's dominant? That's what I want to quickly show here. So how do we know that 1 is dominant? Okay. I also want to make it clear that 1 will be the spectral radius in this case. If A is column stochastic, then the spectral radius must be smaller than or equal to 1. So 1 is also equal to the spectral radius of A. So the spectral radius is an eigenvalue. It's equal to 1 and has a strictly positive eigenvector. Okay, so how do we know this? Well, we know this because we know that 1 is a spectral radius. So if this is the complex plane, then all of the eigenvalues are contained inside the circle or on the circle. We want to show that none of the other eigenvalues will be on the circle. So none of the others will have modulus 1. We want to show that all other eigenvalues must be inside the circle. Okay, so because A is strictly positive, that's what we assume here, we can find a small positive real number epsilon such that A minus epsilon times the identity matrix is still strictly positive. Right? And the set of eigenvalues of A minus epsilon times the identity matrix will be equal to the set of eigenvalues minus epsilon. This is quite, and by this I mean we take each, this is a set and we subtract a real number, and that means we take each element in this set and we subtract epsilon from that. So this is the set consisting of lambda minus epsilon such that lambda is in the spectrum of A. So this is the translated set. Well, we translated, we moved it, we shifted, and then so we see that the spectrum of the matrix A minus epsilon times the identity matrix must be inside the circle if we just shift this one by epsilon to the left. And we know that the spectrum must now be contained inside of this matrix, A minus epsilon, must be contained inside this circle, which is centered at minus epsilon. Okay, but this is still a strictly positive matrix, and because it's a strictly positive matrix, we know that the spectral radius, and that's also something which the Perron Frobenius tells us, the more general version, the spectral radius is an element of the spectrum of the set of eigenvalues. So that means this point here, 1 minus epsilon, is the spectral radius. And that means that this whole set of eigenvalues of A minus epsilon times the identity matrix must be contained in the circle with radius 1 minus epsilon. So that's the smallest circle. And now we can shift this back again, because we know that this spectrum of A is equal to the spectrum is the set of eigenvalues, sorry, is the spectrum of the set of eigenvalues A minus epsilon times the identity matrix plus epsilon times the identity matrix, which is equal to the set of eigenvalues of A minus epsilon times the identity matrix plus epsilon. And that means that if the spectrum of A minus epsilon is contained in the smaller spectrum, then the spectrum of A must actually be contained in a smaller circle centered at epsilon. And that means, sorry, my circles are not very round, but that means that all eigenvalues of A, they must be inside or on this red circle, and those numbers, except for the 1 there, all have modulus strictly smaller than 1. So we conclude that the modulus of lambda is smaller than 1 if lambda is an eigenvalue of A and lambda is not equal to 1. So 1 is a dominant eigenvalue of A if A is column stochastic and strictly positive. Okay. Now back to Google. So Google and the PageRank algorithm, maybe I shouldn't say Google, but Google, the PageRank algorithm is a little bit more complicated because it also caters for the case that there might be some websites with no outgoing arrows, and it might be that the graph will not be strongly connected. And because of that, we make a little bit of a change. So if we have, for instance, like this case, we have website 1, website 2, like this, and website 3 and 4. So website 3 links to 4, 4 links to 3, and 1 links to only 2. Now, this is not a strongly connected graph, and also there are websites with no outgoing links and also no incoming links. So now we have to assume in the real world that happens, there are websites with no outgoing links and also with no incoming links. Now, if a website has no outgoing links, the assumption is that someone who surfs the internet and arrives at that website will still somehow visit the next website, and the assumption is that he will enter an address and it will be entered at random. So in this case, we will have a matrix like this: 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. Now we see we have a column of zeros here. And what do? Well, we assume that if we are at website 2, which has no outgoing arrows, then we will visit any website at random next, and we're going to assign a quarter, a chance of a quarter of visiting any website because it will be at random. So instead of writing the matrix like this, we are going to write a quarter, a quarter, a quarter, a quarter in this column here. Furthermore, we are also going to assume that at any point in time, someone surfing the internet could pick a website at random and not follow a link, but just pick one at random. And we are going to say that the chance of that happening, or that might happen in like 1 minus alpha of the cases. So there's some number alpha, which should be greater than 0 and smaller than 1. And we multiply our matrix by alpha, and then we add 1 minus alpha times the matrix, which just consists here of 1 over 4 for all of its entries here, where we have 4 web pages, and that means this is for this random jump to any other website, no matter where you are. And if we do this, okay, then alpha and 1 minus alpha are both strictly positive numbers. The website, this matrix here is strictly positive. So we add this to this non-negative matrix, and we end up with a matrix, let's call this G, which is strictly positive. And that's the matrix which we will use in our algorithm. And that matrix will, if we reapply it, we start with some vector x0, which is which has positive entries and they sum up to 1. Then if we take G and we apply to this vector and we reapply it, then this will converge to some positive vector x, which will give us the rank. And if we start with 1, which sums up to 1, then x will also sum up to 1. And so this will be a vector, in this case where we have 4 pages, will be x1, x2, x3, x4. It will be strictly positive, and that will give us our rank. And because of Perron Frobenius, we know that this will always converge to a unique vector, giving us a rank. And that is my talk. I want to show a little bit more complicated example as well, which comes from a thesis called Mathematik hinter Google by Matthias Frick. There we have a little bit of, we have 7 web pages. They are also, this graph is not strongly connected, but using the little trick, they are also like web page 3 has no outgoing links. That's why 1/7, a column of 1/7 is added there in column 3. And then a damping factor alpha is applied. And in this case, we have this matrix of entries 1/7 because there are 7 websites. And then we obtain the matrix G. And if alpha is 0.85, then this is what the matrix G looks like. And then if we start with the vector 1, 0, 0, 0, 0, 0, 0, and apply this matrix to this vector multiplied with this vector, then here are the, well, here's x1, so that is just G times x0, and x2 is given here. And then we see when we get to, after 41 iterations, we don't see a difference anymore if we take the numbers up to 1, 2, 3, 4, 5, 6 decimal places. So then we have reached the ranking vector up to quite a good accuracy. And that's kind of how the Google algorithm works. Although today we know that no one really knows how the Google algorithm works because it's much more complicated now. But some of this is still there. So I'm finished.